first letter uniformly distributed? No, alright, no, it's not uniformly distributed. You can see that certain letters appear much more than others, right? If you have a certain hash function which gives you the first letter, and then the first letter happens, certain first letters happen much more than others, then you're going to get clumping behavior, right? Clumping behavior, and that's not good, right? That's not one of our desired data. Okay. All right. So let's look at a different hashing function. Maybe we try this, right? Maybe we say, all right, since the first letter didn't work, I'm going to do a sum of all the letters. I'm going to sum up all the letters. So if it's just a string, I'm going to sum up, 8 plus 1 plus 2, and I'll just get the number associated with a particular letter, and I'm going to sum it up. Okay, so H is the 8th letter, A is the first letter, so on and so forth, and then I sum up the value, and this is going to be my hash. Okay, this is going to be my hash. Again, let's try to think about whether it evaluates, it satisfies all these criteria that we want. So, do you think it's a good hashing function? A, yes. I think this is a good hashing function. B, no. No. People say no. And maybe? No. Okay, so a lot of people are saying no. Right? Some people say maybe. The right answer is no, it doesn't. It doesn't because, well, a few things. One, the word length, right, is dramatically affected by your word length. If your word is longer, then in general the hash will be larger, right? And the word length here in our English language is not that long. Okay? There are certain words, word lengths, which are much more frequent than others. All right, you can just read the text and you can find all the words. Certain word lengths are just significantly more probable than others, and you can see this in other languages as well. So this is an example for Finnish. Right? Okay. The other bad thing is that anagrams actually have the same hash value, right? God and dog, they will hash the same thing because you're just summing up all the values. Okay, so this is not a good hashing function. So what we really want is that we want hash functions that kind of look random. Okay, they kind of look random because you can think of random numbers as uniformly being generated, right? So uniformly across a range, let's say, right? So we want hash functions that have this kind of behavior, right? That you give a string, you uniformly just picks a pocket, right? So this is similar in concept to a pseudo-random number generator. So most of you know what pseudo-random number generators are. It's RNG. So every time you ask your computer for a random number, it's not a real random number, right? It's actually pseudo-random number. So pseudo means fake. So it's not really random, not really drawn arbitrarily by using some what do you call it, cosmic rays or something, although some people might do that. It's actually computed. It's computed. So one popular way of generating these random numbers, pseudo-random numbers, is called the linear congruential generator, LCG, right? And it follows this formula. Okay. Basically, the next number that you generate is some multiplication of the previous number with some constant plus some constant term, and then modulus by m. Okay. And then if you choose A, C, and M properly, you can actually get LCGs that can pass tests of randomness. Okay, so this is the formula. And you have to choose A, C, and M properly, but if you can do that, then you can, when you start running this in a sequence, it will actually produce numbers that appear to be random. Okay, but they're actually not, right? They're generated using this process. Okay, they're deterministic, but they appear to be random. Okay, so based on this idea, we're going to look at certain hash functions today that kind of look like this, but not quite. Okay, we'll look at that. And then there are two techniques. First division, and then multiplication. We'll cover division first. Okay, so the division method is extremely simple. Extremely simple. Okay, the hash is just simply this. We're going to take the key and one m. All right, we're going to pick some m. So we're just going to take k modulus m. So we take the remainder. All right. So let's just say m is 7 and h is 17, you get 3, right? Because the remainder, 7 times 2 is 14, and then your remainder will be 3, right? So if m is 20, h 100 is 0. If m is 20, h of 97 is 17. If m is 13 and h is 102, hard to compute in your head, it's 12. Okay? So the two things collide, K1 and 2 collide, if they have basically the same remainder modulus m. Right? So that's when they collide. So how do we pick m? Alright, how to pick it? So there can be different choices. Let's start with one choice. Let's make it a power of 2. Okay, let's make it a power of 2. So the very, very nice thing is that it's very fast to compute k mod n. Right? It's very fast to compute. Why is that? Why can I calculate mod 2x very, very quickly? Yeah, I can do shifts, right? I can calculate division and multiplications via shifts, right? So which of these formulas would work, right, for computing k mod n? All right, so why don't you try giving it a go? I'm going to the, I don't know why, but poll everywhere is not giving me the right thing for this answer. I don't know why, but try to figure it out, okay? All right. So I'll give you a couple of minutes. I'll put it here, all right? So base your answer on what is written here and not in poll everywhere, okay? I'll give you a minute. Just 1 minute, and put your answer into poll everywhere, which you think is a formula. So everyone knows the shift operator, right? So k shift x means that I'm going to shift k by x, x spaces, right? And that's equivalent to a multiplication by 2, x times. Okay, time's up. Let's look. So we have a bunch of answers. 4 answers, actually, not many. Okay, 4 answers, not enough. Do you need more time? Okay, so I'll give you another minute. Let me just clarify what shifts are for you to look for shifts. If you shift to the right, you're doing a division. If you shift to the right, yes, you're doing a division. If you shift to the left, you're doing multiplication. Okay, so for example, 9, this is the binary sequence for 9. Okay, binary representation for 9. Divided by 2, I'm just going to shift by 1. Okay, 2 is 2 to the power 1, and that's going to be 4. Alright? If I want to divide by 4, that's 2 to the power of 2. I shift it twice, and that's going to be 2. Alright? If I multiply, I just shift it to the left. Alright? So I'm going to shift these digits, I'm going to push it, and then add a 0 at the end. Alright? That's going to be 18, and then you shift it twice, and you get 36. Okay, you add 2 zeros at the end. Alright? So that's shifting. So if I want to do a k mod m, what do I have to do? So I'll give it another minute. So you can evaluate each one of these in sequence and see which one gives you the right answer. Okay, so let's have a look. 16 answers now, okay. So 17, good, so more answers coming, great. Most of you are saying it's D, few of you are saying it's B, and this is the wrong answer, of course, but this is just shifted left first and then shifted right after, alright. Okay, so most of you are saying D. Let's have a look at the right answer. The right answer is D, you're right. Okay, most of you are right. Okay, so why do you need to shift right and then shift left and then minus? What are you interested in when you're doing the remainder? Are you interested in the higher order bits? No, you're interested in the lower order bits, right? The lower order bits are the ones that are going to give you your remainder, all right? So the way you get your lower order bits, right, is to shift it to get rid of the lower order bits, and then you take a minus, right? Then you get your lower order bits. Okay. Okay. So this is fast to compute. That's nice. All right. But does it satisfy our desirability? So what do we want? Remember, consistent, fast to compute. See, it's the first two. All right. We know it's fast to compute. We know it's consistent. But does it scatter the keys into the buckets as uniformly as possible? Right, that's the question. So what do you think? Do you think that it scatters the keys into the different buckets? All right, so AES, B no, does it? You, C maybe, okay. D asks Naruto says B, okay. So as you might find, Naruto is right, the answer is B, right? The answer is B, but why? Why is the answer B? Right? Why is it that this method doesn't scatter the keys very uniformly? So the reason is that here's an example when this doesn't happen. Imagine what happens if all the input keys are even. Okay, if all the input keys are even, this could happen. If all the input keys are even, then K mod M must be even. Okay, this must be the case. Why is it so? Now, this K, right, the key is some quotient plus your remainder, right? Something times M plus your remainder. That's by definition. Okay? So we know that this is some multiple of M, all right? And M is even, all right? 2 to the power x is always even. So this is the remainder. So this part is even because I said the key is even. This part must be even, right? Because it's a multiple of M. How about the last bit? The last part, the remainder. Is it odd or even? It must be even, right? This part must be even. Because this K is even, IM is even, this part must be even, right? Even number plus an even number, you get an even number, right? Okay. So this is not great because it means it's no longer uniform, right? It means that every time I give it an even number, it's going to give me an even bucket, all right? And this is going to waste half the space, right? It always just uses, it will never hash to an odd bucket, which is not good, all right? We're going to waste half the space. So this is fast to compute, but it doesn't use a table. And it also uses the lowest order bits, and we've already discussed this. Okay? So let's talk about division in more general terms, right? If K and M have a common divisor, D, right? So the key and M, right, the table size, have a common divisor D, then what property can I say about the hash? Right? What can I say about the property of the hash? If K is divisible by D, IM is divisible, definitely divisible by D because we have common divisor D. What about this value over here? Right? So how much of the table do we use? And then extrapolate that into answering this question. How much of the table do you use if both X and M have a common divisor D? Alright, so X here is the key. Okay. Is it D, 2D, 1 over D squared, 1 over D, and E? Okay, let's so extrapolate from your previous, we looked at it when it was even. Now we say it's a multiple of D. Even is just a multiple of 2. It's a multiple of D. In the previous case, you used only half the table. In this case, how much of the table do you think we'll use? Right? So let's have a look. One answer so far. 2 answers. Again, I'll give you a minute. Okay, 1 minute's up. Let's look at the answer. So we have 15 respondents so far. Most of you are saying 1 over D, right? Some of you are saying D. Let's have a look. So the right answer is 1 over D. 1 over D from the table. Because your hash must also be divisible by D, right? It must also be divisible by D. So we are only going to use 1 out of every D slots, right, in the particular table. So this is not a good outcome, right? We're going to waste a lot of the space in our hash table. So we're going to have to choose M. So what are we doing is we're going to have to choose M so that it has no common factors with any of the K, right? We're going to have to choose M so that it satisfies this property. So what kind of M satisfies this property? Prime, right? We choose M to be prime. Okay, we avoid powers of 2 and powers of 10, alright? And in practice, this is very popular, it's very easy to do. It's not always the most effective in practice, but it's used a lot, okay? It is, however, slow. You can't do shifts anymore, right? You no longer have this 2 to the power x thing, so you can't do your shifts anymore. But it works well, okay? You can use the table very well. Alright, let's move to the multiplication method. Alright, so the multiplication method is a little bit more complicated. Alright, we're going to first fix a table size, alright, which is 2 to the power of r for some value r. We pick r, okay, and m is going to be 2 to the power of n. Alright, so we know the word size. The word size is just going to be the size of the key in bits, right? And you imagine that that's given to you, alright. And we're going to pick some constant a, right? The requirement for constant a is that it has to be in between 2 to the power of the word size minus 1 and 2 to the power of the word size. Okay, it has to be a large number basically in terms of the word size. Alright, so that's the requirement. After we pick these things, we're going to compute the hash like so. We're going to multiply a times the key. We're going to multiply a and the key together, and then we're going to mod the table size as usual. Right? We're going to mod the table size, and then we're going to do a shift. Alright, we're going to do a shift in order to get our bits. Alright, so that's what we're going to do. So this is what the operations look like if I were to draw them out. Okay, so here, keep in mind that I'm drawing the bits here. Alright, so when I compute AK, this equals means that the size of this is 2W bits. Okay, it's not equals to 2W. Alright, it's the size of it is 2W bits. Okay, so when I multiply AK together, I'm going to get a certain value which is 2W bits long. Then I'm going to modulus 2W, alright, which will give me this part, alright, which is W bits long. That's also a bit too big for my hash table. Right? Hash table is 2R, size of 2R. Right? So I'm going to shift, right? I'm going to shift it, and this is going to give me my R bits. Okay, when I shift it left, this part's going to drop off, and I'm going to leave left this part left. Okay, so that's going to be the setup that I'm going to use. Okay. Everyone clear the multiplication method? It's slightly complex, but it's not that hard. It's just a step-by-step process to go from you're going to first multiply to a larger number, and then you're going to shrink it down in order to get a value that you can map to your hash table. Okay. All right. So here's a question: for the multiplication method, should A be even or odd? Right. So A, yes, it should be even. B, it should be odd. C, neither. D, what if I told you the sentence never even or odd is a palindrome? What do you think? Alright, so what do you think? Do you think that, oh okay. Should it be even or odd? Right? Should A be even or odd? And let's just put your answer, I'll explain why, whatever it is in a second. Do you think it should be even or it should be odd? Let's have a look. So I'm going to put it back here so you can have a look at this formula. Start thinking about what happens when A is even. Start thinking about a situation when A is odd. You can't be neither, I guess, unless it's 0, which maybe is not so good. Alright, so have to think. more seconds. Alright, so most of you are picking never even or odd is a palindrome, which is true. The other best answer is odd, right? And then a few people are picking neither or even. Alright, so let's have a look. So A should be odd. Alright, let's talk about what happens when A is even. Okay, let's see what happens when A is even. So when A is even, right, you're going to multiply. A is even, so it's 2 times something, say, alright? And you multiply some even number. What happens here? What happens when you do an even multiplication? You are shifting. Multiplication is shifting. You're shifting. And what happens when you shift? You have zeros added to the back. Alright? Then you add to the back, and then you do a modulus in order to get the value here. What happens to this? Think about that. We are wasting, again, we are going to waste space. Okay, we're going to not use the hash properly. This does not result in a good hashing function. Okay, so don't pick A to be even. In practice, we have to choose A and R very carefully. Okay, A is often chosen to be odd. Donald Knuth recommends A equals to this value. This value. This value is related to the golden ratio. Right? The golden ratio. By the way, how many people here have heard of Donald Knuth before? Oh, okay. So he's again one of our famous computer scientists. All right. He wrote a very famous textbook for the art of. It's not a textbook. It's like a series of textbooks. The art of computer programming. It has almost everything you ever want in about algorithms in there. So if you're willing to go through it, this is a textbook. Like this is the Bible, right? The Bible of computer science. Well worth looking into. Okay. And also the benefit of this is that you can do very fast, right? Very fast shifts. Okay, so we've covered 2 different ways, right? Division and multiplication. These 2 ways, if you choose the numbers correctly, you can get a consistent, fast compute and pretty uniformly distributed. Because your keys can be pretty uniformly distributed across your products. Okay, but you need to pick the values appropriately. Okay, you can choose either one in practice. Okay, it depends really very much on application. All right. In general, good hash functions are typically notoriously difficult to design. You can come up with a hash function you think is good, and then use it in practice, and you realize some weird stuff comes out because of data distribution. Okay, so good hash functions are very hard to design. There are some very common ones that you can use already that comes with your standard libraries. Okay, use those first. But if you really have to design something yourself, then keep in mind that this is not easy. Okay, and there are high level courses that you can look into how to design good hash functions. All right. So let's move on to the second topic, and the second topic is how to pick the table size. Okay, so remember that for now, let's assume that we're doing hash chaining, so these separate chaining. We're going to assume 2/2 for now. All right. In that case, then our expected search time is this, right? We proved it yesterday. All right. So the optimized size is some constant of n, right? The optimum table size m is some factor of some multiple of n, right? Now, if m is much smaller than 2n, right? If m is much smaller than 2n, what happens? You remember yesterday we said the load factor should be right? So if it's worse than that, what happens? Sorry? What's the thing that we want to avoid in hash tables? Collisions, right? If your m is too small, if your table is too small, you're going to have too many collisions. Okay? If your m is too big, what happens? Yeah, it's wasteful. You use too much wasted space. So by analogy, you can think of it as like gas molecules in a container. All right. So if it's a sealed container, so if your sealed container is small, right, the molecules are all going to be bumping to one another, right? There's a lot of collisions happening. But if your container is big, then yeah, the molecules won't really bump into one another, but there's a lot of wasted space. All right. So we want to have a table size which is kind of just right for the number of molecules that we have. Okay, that are bouncing around. The problem is that we don't really know what n is in advance. Right? We don't know how many keys. So what we're going to do is we're going to deal with it on the fly. If you will. We're going to grow and shrink the table size as necessary. So have you heard of this idea before, growing and shrinking the table size? Yeah, we looked at it from lecture 2, right? We talked about dynamic arrays, and I mentioned this like amortized constant time, right? What is this amortized constant time? Okay, so today we're gonna reveal what this means, okay, in the context of hash tables, and we're going to study what amortized means in a formal sense. So what we're going to do is we're going to basically have dynamic hash tables or dynamic table sizes, okay? Initially we set the table size to some constant, to some value, m1 equals to 10, let's say. And then after you get certain numbers into the table, then you grow it. The table is too small, then you grow it. Alright? If you delete items, then your table becomes too big, you shrink it. Alright, so very simple idea. When it gets too full in there, you just grow it, and then when it gets with the number of items inside too small, you just shrink it. Okay, to save space. We won't focus on the shrinking part because analyzing both together is quite heavy in the lecture. You'll see that. So we'll focus only on growing the table. Okay, for growing the table. So what we're going to do is we're going to choose a new table size, m2, which is bigger than m1, right? And then we're going to copy all the elements from the old table to the new table. This will not work. Why won't this work? What's the problem with this approach? Yeah, good. So the hash function depends on the table size. Remember, we were looking at the multiplication, division method. The hash function itself, m is in the hash function, right? It's a parameter of the hash function. So if you're just using copying the table, the elements over, right, into the respective places, that's wrong. You're not using the right hash function anymore. So the right approach actually is to choose a new hash function as well, h2, all right, which often will depend on m2. All right, and then we're going to recompute the hash for each key. All right, we're going to recompute the hash for each key. We'll find the appropriate button and put the key value padding there. Okay, and we're going to do that for all of our O elements. How long does this take? So let's try to break this down. How long does this take? So we are first going to have to create a new hash table, right? And this, if you do it like, if you imagine a cell, we have to initialize each cell, let's say, that's going to take us on the order of OM2 time. Alright? Then we're going to have to go through our old hash table, right? And check, right? Is there item here, is there item here, is there item here, is there item here? That's going to be OM1 time, right? And for each of the items that we find, we're going to have to copy it over, right? So that's going to be O n time. Okay, for all the elements that we've already added to our hash table. So in total, we are going to get m1 plus m2 plus n. Okay, if it is the case that m2 is bigger than m1, which is where we are growing the table in that case, then it's going to be O of m2, right? We can drop the m1 because we can say this as, if this is true, then it's 2m2, then we can drop the constant, right? If m2 is some factor of n, right, then it just becomes On, because if this is some Cn, for example, then we can just drop it, right? Okay, so this is growing the table, right? In general, however, we will be using this formula, okay, for the next few slides. Okay. Next question: how fast should I grow? Okay, there are many ways we can grow the table. Maybe we can increment it by 1 each time. Every time it's full, I'm just going to make it grow by 1 cell. Okay? Or I can double the table size, so when maybe it gets to full, then I'm just going to double it. Okay? Maybe I need to square the table size. So, doubling is maybe not big enough, maybe I need to square it. Right? So from, in this case, right, from 5, I think I'm going to square it up. Right? Okay. Bigger than that, 25. I'm just lazy draw. Okay, so can we figure out which way is the best way? So which do you think is better? Do you think it's better to increment by 1, double the size, square the size, they're all the same, or they're not the same but you're not sure which one? So how many of you think that this is just a quick poll, right? So how many of you think we can just increment by 1? That's good. Doubling? Oh, lots of people. Square, if double is better, double is bigger. Square is even bigger, so maybe it's better. No? Same, all the same, doesn't matter what we pick, will work. Definitely not the same, but kind of not sure which one might work. Oh, so a lot of people are actually picking the doubling. Okay, so let's have a look, one by one. Alright, this part is going to get a little bit heavy, so I'm going to go a bit slow, but just stop me if any of you are lost. Okay? Alright, let's look at increment by one. We're going to look at CI. Right? I'm going to denote CI as the cost of the ith insert. Okay, it's the cost of the ith insert. So there are two possible cases that can happen. Alright? One is the table is not full. If the table is not full, then I'm going to just the cost is just one. I'm just going to put it inside. I'm going to assume that I'm only going to I'm going to increment my table size when it gets full. Okay, that's my assumption. I'm going to increment it, I'm going to grow it when it gets full. Okay, this doesn't have to be the case in practice. Okay, this is for easier analysis. All right. So the case that the table is not full is easy. I just put the thing in. All right, let's take one. If the table is full, I need to do something else. I need to grow it. I need to expand the table. Right? I need to expand it by one. All right. So that's going to cost me more. Yeah. So remember the old form, what we derived a couple of slides back. Right? How much effort does it take me to grow the table? I don't only just have to declare new space, right, a new table, but I also need to start copying stuff over, right? And that's going to be expensive. So this is the cost of my new table. I'm going to grow it by one only. Okay. So this is the new table. Okay, cost for new table. This is my old table size. Remember that I have to go through my old table one by one to check whether there are items there or not. If there are items, then I have to copy it over, right? And then I'm going to insert my new item. Okay. So if you sum this all up together, you get something like 2R. Right? You get 2R. Right? So it's going to be more expensive when I have to grow my table, as you might expect. Right? You're going to have to grow your table, so it's going to cost you a bit more. So let's just say n naught is the initial size of the table. Let's just say, okay, n naught is the initial size of the table. I'm interested in the total cost to insert n elements. All right, where n is going to be larger than my initial table size. Right? That's what I'm interested in. So I'm going to start you off. All right, and then you're going to do the rest. Okay, I'm going to start you off. Oh my God. So this is going to be my cost for inserting n elements into my table. Correct? So I'm just summing up the cost from I equals to 1 to n. So first item, second item, third item, I'm just summing up all the costs. That's going to be upper bounded by two portions. Right? By two portions. The first portion is going to be how much it's going to cost me for putting in the first m naught minus 1 elements. Right? So this is when the table is not full. So how much is CI in that case when the table is not full? 1. This is easy, right? This is 1. Okay. This second portion is when the table is full. So because once you get past M0, every time you insert a new item, you always resize. Right? You're going to have to resize. Right? Because you only increment it by 1. So the next time you put in something else, you're going to have to resize again. Right? So this is going to be this cost. So you can imagine that you want to plug this part in here. Right? Next, you're going to have to bound this. Okay, you're going to have to bound this and try to figure out what order this is in. Right? What's the big O for this? Okay, so you're going to have to make use of the little summation here that you probably know about. Right? This is a simple arithmetic progression, right? Arithmetic progression, and you're going to use that in your derivation. So I'm going to give you, let's say, 3 minutes. Okay, work your way on from this. Okay, try to get like a bound, right? Like something like O n, O n squared, O 1, what might it be? Okay. Okay, you have about 3 seconds, 2, 1, 0. Alright. So let's take a quick poll. How many people think it's AON? ON squared, ON cubed, N log N. Looking at the slides for the answer. Alright, so let's break this down and try to figure things out step by step. So if I were to derive it, right, this is what it might look like. So I know that if I sum up and all this is 1, right, it's going to be bounded by M naught. Right? It's just summing up 1 to M naught, so it's going to be bounded by M naught. Okay? And then I'm going to have to bound this portion. I'm substituting my 2i, right, here into this here. Right? I'm going to take the 2 out. Okay? All I'm doing is taking the 2 out. Okay? This leaves the 2 on the outside. And this is just going to be the sum from M naught to N. I'm going to simplify, start my life, and put 1, right, over here because it's bounded. I mean another change here. M naught is smaller than N, right? So I'm going to put N. And I know that this is going to be upper bounded by N plus 2, the summation from I equals to 1 to N. So I'm just summing up extra stuff again. I'm going to make use of my little formula here. Plug it into the equation, alright? That will put half N plus 1, the 2's cancel out, and that's going to be ON squared, alright? So this is the right concept, alright? So it's going to be ON squared. So it's ON squared. What is the average? I'm going to use this word amortized now, I'll define it later. Average cost per insert over the sequence, okay, over the entire sequence, alright? So what is the average cost per insert over the entire sequence of N inserts, okay, of N inserts? So, what do you think it's going to be? Sorry? Constant, good. Oh no, sorry, O-N, not constant, O-N. We'll get to constant later. O-N, alright? Why O-N? Why? Right? It's because the average cost is simple. It's just going to be 1 over N, right? Your total cost divided by N, essentially. Your total cost divided by N. Okay? And that's going to be, you just plug this guy, right, inside here. Okay? And it's 1 over N. You cancel out the N's, and that's going to give you ON. Okay? So all we're doing is we take the total cost, divide by N. That's going to be our average cost for the entire, per insert for the entire sequence. Okay? For the entire sequence. So that's the total cost for inserting N elements is ON squared. What we call the amortized cost is going to be ON. Right? This is not so good. Right? This means that I maintain my hash, so if I put N item, it's going to be N squared. Not nice. N squared is not that pretty. Especially since we said that insert should be what? O1. Okay, so this is not so great. Okay, now let's move on to the second thing, doubling. So we're going to do the same trick, alright? We're going to analyze it the same way, but doubling requires a little bit extra, we'll see. So we begin, we're going to say what is the cost of the ith insert, that's we're going to start there, alright? So if the table is not full, then it's easy, we just put the thing in and that's going to be cost of 1. If the table is full, we're going to have to grow it, okay? When we grow it, what size are we going to grow it in, right? So 2 times however the size is now, right? Okay, so it's going to be bounded by 2i plus I minus 1 plus 1. Let's say that's 3i. Okay, that's bounded by. And the table is full only when I is an exact power of 2. Okay, we don't need to grow every time. Okay, we only grow when I is an exact power of 2. Right? Because it only gets full at the point. Alright? So that means that I is to the power of j for some j. We don't know what j is, but that's some value of j. Okay? And again, we say that m naught is the initial size of the table. So again, we're going to analyze what is the total cost to insert n elements when n is bigger than m naught. Okay, that's our goal. We want to analyze this total cost. So I'm going to start you off again. Okay, I'm going to start you off again and say that look, all we're going to do is just we're going to sum up all our costs from I equals to 1 to n. This is what we're interested in. This is the value that we're interested in. We're going to bound this value, upper bound this value. Again, we're going to say, okay, this is the cost basically to insert elements 1 by 1, right? In the times that I'm going to not have to expand essentially. Alright, I'm going to just sum this all out. Okay, and that's going to be bounded by n. Alright, that's going to be bounded by n, of course, because there are only maximum n elements. And this is the portion that I need to take account of for every time I expand. Alright, so this thing, let's analyze this a little bit. Why does it look like this? It looks like this because the cost only happens when? It happens only when I equals to 2j for some j. Okay? Now, you notice that I don't need to grow each time. How many times do I need to grow? So this j will be some value, right? To the power of something, up to some value, right? What is that value? Now to compute that value, we use a trick that we see a lot. Okay, I want to find j, right? What's the maximum value of j? What do? I take logs. Okay, so there are only going to be log n times that I'm going to resize. Alright? And each time of that, I'm going to have to compute the cost of that resize. Okay, so these are my inserts. This is the resizing that I have to do, right? And each time I do the resize. Alright. Now, can you compute this? Can you compute this? I'll give you a minute. Alright, I'll give you 4 minutes, let's say, 4 minutes. And try to finish this off, right? Again, you want it in terms of n, so it can be like O of n, O of n squared, O of n cubed, O of n log n. What should it be? Right? What should it be? And you probably need this little guy up here, right? And this little guy tells you that the sum of 2 to the power of k from k to 0 to log n is bounded by 2 times n. About a minute. Okay, so time's up. Let's get bold. Can someone give me the answer? What do you think it is? Oh, someone said something. You. O-N. Okay, so here's the derivation, right? We're just going to plug in the values that we already know. This is just going to be 3i, right? So it's going to be 3 to the j. Okay, we're going to take the 3 out. This summation, we're going to use this bound here, all right? And this is going to be 3 times 2n, right? It's going to be 6n, and that's going to be O-n, all right? Okay, so that's the bound, all right? It's O-n, which is quite nice. What is the average or amortized cost if it's O-n? Sorry, O1. Good, O1. So why? Again, we do the same trick, right? We take that, to compute the average cost, is simply the total cost divided by n. Total cost divided by n. We know what the total cost is. The total cost is 7n, right? And then you divide it by n, and that's going to give you 7, which is O1. Alright? So that's basically how we do this. Okay, so doubling the size is great. The total cost of inserting n elements is On, and the amortized cost for an insert is O1, right? Which is what we say would be a nice property of hash tables to have. Okay, so this is not bad. Right? This is pretty good. This is what we expect. Okay, look at the squaring. I'm not going to make you do all that again. All right, so it's on the slide. You want to have a look. It gets a bit hairy for squaring because you need to take you sum up from log to n. It grows very big, right? Very fast. So it doesn't grow very often, but when it grows, then it grows very, very big. Right? So in this case, however, it's also O(n) squared. All right? And when it's O(n) squared, you know that the amortized cost is going to be O(n). All right? And this is also not so great. Okay. So what you want to do is you want to double the size. It's not too fast, not too slow. Okay? And this gives us the nice amortized average cost per insert that we like. Okay, for hash tables, which is constant time. Okay. So I want to clarify certain things here because we've been talking about average cost for a second, but perhaps in the average cost, there's a little bit different from when we were talking about quicksort, for example. Okay? So the worst case cost per insert is what? What is the worst case cost per insert? O(n), great, it's O(n), because there's a chance that at that insert you're going to have to resize. Okay? But the average or amortized cost over a sequence is O(1). So amortization, when you talk about amortization, you're not talking about a specific operation. You're not saying that this insert, the fifth insert, is going to cost me O(1) time. You're not saying that. It could take O(n) time, right? But you're saying, what is the overall cost of an insert, right? The average overall cost of an insert over a sequence of operations. So if I do, let's say, m inserts, all right, then what is the average cost of per insert? Right? That's what I'm interested in for amortized analysis. So it's a little bit different in terms of interpretation. So you have to keep that in mind when people talk to you about amortized analysis. Okay, on average, the different ways of talking about what this average is. Okay, in the analysis that we've done before, average sometimes can be average over the inputs, right? So any kind of input on average, it's going to give this kind of bound, right? This bound pole. In this case, it's not, right? It's average for a sequence of operations or any kind of sequence. Okay. Now, it's also a worst case analysis, right? It's not a best case analysis. This is it's an average worst case analysis. Okay, you have to keep that in mind. Another thing is that it's a very common kind of analysis in data structures. You will see more of it later on. There are three kind of techniques for doing amortized analysis. The first is aggregate analysis. We just did that. Okay, aggregate analysis is when you take the total sum over the entire sequence and then you divide it by the number of operations that you did. All right, that you need to do, and that's aggregate analysis. The second is called accounting, or the banker's method, and the third is called potential, or the physicist's method. And we're not going to talk about potential, we'll talk about accounting today. All right, we're just going to talk about accounting today. This whole part of amortized analysis, since when we start talking about dynamic table sizing, it's kind of to give you an intuition. We're not going to be we've not been and will not be tremendously rigorous about it. Okay, you'll get that when you get up to your higher level courses. But for now, I want to give you a flavor and an intuition behind it. So why we're doing this and how we go about doing it in terms of strategy, please. Okay. So let's start with a definition. Okay. The analogy is like to paying rent. Okay, for the accounting method. How much do you pay rent? Okay, this may not be a great analogy then. Okay, you pay school fees, right? Or your parents pay school fees maybe, I don't know. Okay, so you don't pay school fees every day, right? You pay school fees maybe once every semester or one every year, right? You don't pay it every day. So, like rent, you only pay it a certain time, right? At a certain time. And you hope that you earn enough money every day so that when it comes to pay rent, you pay rent and you still use that amount. So what happens is that you earn some money, let's say I earn some money, okay? And I need to spend some money for my daily expenses, right? But I need to make sure I save enough so that when it comes to pay for my rent, then I can pay my rent, okay? And I keep going forward that way, all right? So my income has to upper bound, right? The sum of my income should upper bound the sum of my expenses, or else I'll go bankrupt, right? That's the idea. Okay. So this amortized cost is going to be, let's say, by analogy, like my income. Okay, it has to upper bound my expenses for it to be valid. All right. Okay. So we're going to define an operation to have amortized cost Tn if for every integer k, the cost of k operations is smaller than k Tn, k times Tn. All right. So let's look at an example. I think this will help to make it more concrete. All right. So I'm going to say that the amortized cost of the insert is 7. Okay, the amortized cost of the insert is 7. So let's check whether this is true or not. So the first insert is going to cost me 5, all right, that's bounded by 7, I'm good. All right, I'm good. It's less than or equals to k times t. This is 1, all right, so I'm fine. The second case is going to be 5 plus 5, all right. That's going to be bounded by 2 times 7, which is 14. I'm still good, all right, I'm still good. Here I'm going to sum up my 3 operations, right, k operations. It's again bounded by k times 7, 3 times 7, which is 21, all right, I'm still bounded. And you can check that this holds for the entire sequence. Okay, so no matter what, I make sure that k times tn must be larger than the sum of all the operations thus far. Okay, so that's what I'm checking. So now, here's a case where I say my amortized cost is 7, right? And the first insert cost me 13, let's say. Okay, cost me 13. In this case, 13 is more than 7. Right? The second case, I add 5. Again, it's more than 2 times 7. This is bigger. This 18 is bigger than 14. Right? Again. But then the third time, it also happens that this is not helped. But by the fourth insert, I'm in kind of positive territory again. Okay, and by the fifth insert, I'm positive territory again. Is this correct? Is it correct for me to say the amortized cost is 7? No, it's not. Okay, why is it not? It has to hold for every integer k, all steps. Okay, all steps. You cannot just hold right at the end or right at the beginning. It has to hold for the entire sequence. Okay, so you must keep that in mind. You must hold for the entire sequence. All right. So we know that, for example, as I said before, the worst case insertion is ON, but the insert operation has an amortized cost of O1 for n inserts. All right. So that's a difference in the meaning of this thing. Okay. So I'm going to again go back to the analogy of paying rent. So you have some bank account, okay, where you're going to store extra money, okay, that you get. Each operation adds some money to the bank account. There's going to be some charge for every operation, okay, and it's going to add some money to the bank account. Every step that I'm going to spend some money also, okay. There's going to be immediate money that I need to pay to perform the operation, and there's going to be some money that I can put in my bank account. That's going to be my savings, okay. So the average, the amortized cost is going to be that charge. Okay, that total charge, okay, my immediate and my deferred. So how much I can save plus how much the actual cost is. Okay, that's going to be my amortized amount. I'm interested in this value. Okay. So my strategy is going to be to select a charge amount for every insert. I'm going to apply these hash tables. Okay. I'm going to select some charge amount for every insert. Right. I'm going to try to ensure that my bank account is always big enough for me to pay for my resizing. That's my idea. Okay. So let's be a little bit more formal for it about this. I'm going to say my actual cost per insert without resizing is going to be CI. Right? That's the actual cost. Right? That's how much I have to immediately pay for my inserts. Okay? Without resizing. All right. My amortized cost or my charge is going to be with a hat symbol here. Hat CI. Right? That's how much charge is going to be. Okay? Now, if my amortized cost is bigger than my actual cost, there's going to be some extra left over, right, that I can use to pay off future operations. Let's say resizing. Okay. So the key, of course, is that remember that I cannot let any sequence go down to negative, so my total credit can never be my negative. All right. I must always make sure that it's always more. All right. So my total credit can never be negative. That's very important to keep in mind. So let's just say I charge, my amortized cost is 2. Okay, I charge $2 for every insert. And then I have to pay $1 to actually do the insert. Okay, but the extra $1 I keep in my bank account. Alright? So after I insert 3 items, I'm going to have $3 in my bank account. Right? I paid $3 to put them into the hash table, but I have extra $3 that I saved in my bank account. Now when I insert my 5th element, what's going to happen? My cost, right, is going to go up suddenly for that insert because I have to resize. Okay, I'm going to have to resize. So I'm going to pay for the insert, but I'm going to have to pay for the resize as well. I can't pay the resize with the amount I'm earning currently, but I have the deferred money. I have the money in my bank account that I can use to pay for this resizing. Okay, and that's what's going to happen. My bank account will then drop to $1, right? I have $1 left, but I paid for the for the resize. This is a way that I can ensure that I are always and always larger, right, than how much I need to pay out. So there are two amounts here by this analogy. There's a deferred dollars, right, which I need to pay for resizing. It's okay, right? All these are just charging one basically per operation, so it's going to be okay, right, in total. The immediate dollars was okay for inserting each element into the table for k elements. And so the total was deferred plus immediate, which is just okay plus okay, which is okay, right? It's okay. And then the average cost per operation, right, is simple. I just look at how much I was charging for my amortization, right, which is 0.1, right? And I was just charging $2, right, for each of my inserts, and that's a constant, right? It doesn't depend on n, right? It's just per operation. It was just a fixed amount. Okay. All right. So let's look at the second example. This second example is called binary counter example. So binary counter is very simple. What you do is you just increment the values in let's say 1 becomes 2, becomes 3, becomes 4, so forth. Okay. And at some point I want to read the amount. So I'm just incrementing and I'm reading. Okay. So when I increment, then I do one increment. It's going to be 1, increment 2, increment 3. So but represented in binary. Okay. Represented in binary. So this is to the power of 0, or to the power of 1, to the power of 2, to the power of 1, to the power of 2 plus to the power of 1. Right? No, sorry. I'm an idiot. To the power of 0, to the power of 1, to the power of 1 plus to the power of 0. Okay? So these are increments. And then I can read. Alright? Now, what's the worst case cost of increments? Right? What is the worst case cost of increment counter if a max value is, let's say, n? Right? The max value is some value n. We'll just do a quick poll. How many? We'll just quickly go by intuition for now. How many people thinks 01? Worst case cost. Log n. Log n. Log n. On. N squared. I have no freaking idea, man. Okay. It's log n. Why is it log n? Why is it log n? To represent number n, how many bits do you need? You need log n bits, right? So some of them, there are going to be some increments which are very, very expensive. The increment that I'm talking about is like this one. You have all the ones, and suddenly you increment it, and then this 0 swaps to a 1, but all the ones have to be swapped to 0. Right? And you have to pay for each of these changes, right? That's very expensive to do. Okay, so you need to make log n kind of these changes, all right? If your number is n, all right? Okay, so the easy answer was log n, right? But let's do a more careful analysis using what we just learned, using amortized analysis. Okay, during each increment, notice that only one bit is changed from 0 to 1, right? During each increment, this happens. But many bits can go from 1 to 0. Okay, many bits can go from 1 to 0. So you can imagine that when you're changing, this is perhaps like akin to the resizing cost just now. There's some huge cost that you have to pay sometimes. Okay. So whenever you change from 0 to 1, I'm going to add $1. Okay, I'm going to add $1 on my bank account. Whenever I change it from 1 to 0, I'm going to pay $1. I'm going to imagine that each bit has a bank account in this case. Okay, each bit has a bank account. So every time I increment, I'm going to make sure that I save $1, right? I keep saving dollars, right? Until I get to the end. And when I get to the end, I'm going to make sure that I have enough money to pay for the switches, right? Because I know that every time I switch it forward, at some point I'll switch it back, right? So whenever I switch something, I have enough money to switch it backwards again. So that means the amortized cost is just 0.1. The amortized cost is always just 0.1, all right? For incrementing up to n. Okay, so that's a taste of amortized cost, amortized analysis. There's more fun in your higher level courses. You can see how to do it more rigorously. Again, this is just to give you an intuition of how to do this kind of analysis, which is actually very useful in practice. Okay, because very often we're not, worst case sometimes doesn't give you a good idea of how your thing's actually performing over certain conditions. It can be too, the upper bound is not valid, right? Not interesting for us. Okay, so let's talk about hash tables. I'm going to introduce you to something called cuckoo hashing. So this is a cuckoo bird. So cuckoo birds are kind of assholes. They don't. Some of them are what we call brood parasites. They don't lay eggs. They don't build nests because having children is expensive. So they just say, I'm going to lay my egg in some other bird's nest, right? And who cares? Let them hang. Let them deal with the baby. Okay. And when the baby is also a bit of a jerk, right? When the baby comes out of the egg, it then pushes the other eggs out of the nest, so that it's the only one they get cared about. It's like the whole this is like evil bird. Not all cuckoo birds are like that. Just several of them, several species of them, subspecies of them. But a couple of computer scientists kind of looked at it and said, hey, good, this is a great idea. This is a great idea for open addressing. Okay, and this is a fairly recent hashing model. Okay, and I'm going to tell you a little bit about it, but we won't do the analysis today. Okay, so you can just sit back, relax, and just try to get a gauge of what we're trying to do. Okay, so cuckoo hashing. What was the big problem with the hashing methods that we've seen before? One of the big problems is that either with probing or linear chaining, is that sometimes you have this case where you have to look through one by one, right? So it's bounded by, let's say, n log n or something like that. Some dot n, right? Sometimes, okay? If you're not careful. For cuckoo hatching, you are guaranteed worst case, not average case. Right? In the previous case, always average case 01, right? But worst case may not be 01. This case is worst case 01, right? Worst case 01. So how do you get worst case 01? Worst case 01, by making sure that each key only has two possible positions. It can only map to two possible positions. Okay? The two possible positions are given by two hash functions, h1k and h2k. Alright? So if I need to look up something, let's say I search for k1, I only check two possible locations. Alright? In this case, let's say h1 gives me 1 and h2 gives me 2. I just check in 1 or 2. Alright? One of these. It has to be. Okay? If it exists in the hash table. I just check it. That's it. Alright? 01 worst case time, because I only check two locations. To do deletions is also easy. I just check the two possible locations and then I delete. Alright? So deletions and lookups are very, very fast. At this point, you might be saying, wait a minute, this doesn't make so much sense. I mean, when I do my inserts, what happens if the two slots are already taken, right? So let's deal with that. So when inserting, if a bucket is already taken, I'm going to push the existing key out. This is like a cuckoo bird, right? If the baby is inside, there's an egg inside, then I'm going to push it out. Okay? So in the same way, this method is going to push keys out, right, to the second location or to the first location depending. Alright? So let's take this step by step. Let's just say I'm inserting key K1. Alright? And the hash H1 says 1. And it's empty. If it's empty, I'm just going to put it there. Okay? So if it's empty, I'm just going to put it there. That's K1. Alright, good. That's easy. Now I insert K6. Now imagine if K6 also gives me 1. Let's just say, for this pedagogical example. Okay? Now, there's somebody inside. K1 is inside. So this technique, remember, is like the jerk technique. So I'm going to kick out K1. Alright? K1 gets kicked out, K6 goes in. Now K1 gets kicked out, where are we going to put K1? So to find out where to put K1, I check my hash functions. Okay? H1 gave me 1 before, and H2 gives me 2. That's it. Okay? So I check, right? I check where my previous position was. In this case, it was 1, right? It was equal to H1, so I can't use this hash anymore. This hash doesn't give me a valid location. I need to use H2. So I put in H2. Okay? I put it in the second position that I'm allocated to. Okay. Now let's just say I put in K7. And K7 says go to 4. Now 4, there's somebody inside, K3. I kick K3 out. Alright? Now I hash K3 again, H1 and H2, and I check. What was my previous location? It was 4, I can't use H1, I'm going to use H2. Now H2 says, let's go to 8. Alright. I go to 8. Unfortunately, 8 has somebody inside. 8 has 5. So I'm going to push 5 out. Okay, I'm going to push 5 out. 5 says H1 is 0, H2 is 8. So 8 was my previous location. Right? I can't use this hash. I'm going to use the other hash, which is 0. I'm going to put it up there. Okay. Now, at this point, some of you may be saying, what happens if you keep, pushing things out, but you keep pushing and pushing and pushing, and you may get into a cycle where, you push other elements out, right? And in an infinite loop, essentially. This is what this is for. Repeat n times. If you repeat n times and it breaks up without having put anything inside, then without having completed, then you're going to have to rehash. Rehash means you recreate the table with 2 new hash functions, hopefully better hash functions. Okay? So you repeat this process until you give up, essentially. Fixed number of times until you give up, and then if you give up, try to put it inside with the current hash table, you recreate the hash table, alright, with new hash functions, and then you insert the element. Alright. So what's the performance of this? The insertions are actually quite complicated, as you can tell, right? You're like pushing things out, and this is busy stuff going on. But actually it takes 01 element times time. Alright, inserts takes 01 element times time. The analysis requires graph theory, and this is a nice segue because then when you come back from recess week, we will be starting with your quiz and then graph theory. Okay? After we're done with graph theory, then we can begin to analyze the Cuckoo hashing method, and we'll talk about that in week 12. Okay? Alright, so that's hashing, right, for us. You now know basically how to solve this problem. You just use a hash table, alright? You want to check who is online, use a hash table. Email blacklist, use a hash table. Represent objects in JavaScript, use a hash table. Patient lookup, hash tables. There are many different applications for hash table. You will get to know them, I'm sure, in your careers. Okay? Alright, hash tables are everywhere. You're gonna see them. Okay, so hash tables are pervasive, they're used everywhere, they're very fast. You can see if you design them correctly, you get this 01 average lookup time, right? 01 search time, very nice. But under optimistic assumptions, probably so in real world often, but it's not perfect. Okay, you have to design them correctly in order to get the performance that you want. And it beats PSTs for searching, but again, you pay for it because you can't do order operations efficiently. You can't do bigger than. Okay. All right. So this was the learning outcomes. If you have any questions, I'll be here. If you have any larger questions, I'll be here. Okay, and I'll see you when you come back from recess week. Okay. Get ready for a quiz.